I'm Casey O'Neill. I am in business development here at RoMan Manufacturing, and I'm joined by my associate, Dave Pridmore, an application engineer. We're in the RoMan Manufacturing studio, and today we want to have a discussion regarding water-cooled transformers, some of the questions that a lot of our customers have about that, some of the concerns, and then a lot of how it actually works and what we do to manufacture our water cooling system for transformers. So Dave, let's get started just by giving us a brief overview of what a water-cooled transformer is and how it works.
Sure. Thank you, Casey, for having me here. So in general, there are three types of transformers. There is an air-cooled transformer, water-cooled transformers, and oil-cooled transformers. RoMan Manufacturing has been in the business since 1980, 40 years. And we have been producing water-cooled transformers at a total of 1.1 million over that time period. Some of the benefits of water-cooled transformers can include a smaller size, greater efficiency, and reduced cost when compared to air-cooled transformers.
So in those 40 years, RoMan has always been building their transformers with a water cooling system.
That is correct, yes.
Okay. Well, 1.1 million transformers is quite a big number. So I would imagine that by this point they really know what they're doing.
Yes, we do.
So back 40 years ago when RoMan Manufacturing started, why did they choose water as their mechanism of cooling?
So the answer is simple. Water is just so much better of a cooling material than air. Water is 23.5 times more efficient at transferring heat than air. And further, given a specific volume of water flow over a component, water has a heat carrying capacity of nearly 3,500 times that of air.
Wow, that sounds like some pretty significant improvements in efficiency over other types of cooling systems. How does it actually work, though?
So in a transformer, which we have here, there are primary and secondary coils. The secondary coil is fewer turns, as shown in this image. As you know, electric current is what creates heat by Joule's law, or I squared R. We have designed our water-cooled transformers with a channeled bus bar in the secondary, the high current, high heat component of the transformer. So as you can see here, we have this channeled bus bar. Now, this is what's delivering the higher current to the secondary, and it's quite an ingenious way that we actually plumb water through the hottest portion of our transformer.
So how much water are you typically pumping through the cooling system in a transformer?
Our transformers are rated at a certain kVA, and when we do kVA testing and rating, kVA is actually a thermal measurement. So it's how much heat that specific current and voltage will make. That heat will generate a certain amount of heat in the transformer, which is rated by its insulation, which is it's at class F rating. So if we look inside a transformer, let's take a look inside this transformer here. So if I turn this around, we have, this is a transformer cut in half. We don't sell them like these. We have the primary.
Would you just get 50% power if you sold that?
One could potentially think, but no, it doesn't work. This is not a working model.
Okay.
This is more for just demonstration purposes. But so we have our transformer portion of the transformer here, and then this is a portion we're going to talk about later. But this is our rectifier diode portion. But these are the turns that you would see in a transformer. So typically in a transformer this size, which this is a 100 kVA transformer, we will pump approximately anywhere between 1 and 2 gallons per minute through the transformer.
Okay. Now, just out of curiosity, how much does that change depending on the size of the transformer?
So,
I mean, does it go to like 10 gallons or 100 gallons, or does it stay pretty close to that?
So we make transformers up in the MVAs as well. So we can make very large transformers for very special applications. But even more of our common larger transformers are around the scale of 400 kVA. But still, the water flow remains the same. It's about 1 to 2 gallons depending on the design. A larger transformer doesn't necessarily need more water flow.
Okay. So based on seeing the water-cooled copper bars, you're not actually encasing the transformer with a water jacket and then running the water through the jacket. You're pumping water directly in, almost in through the middle of the coil.
That's exactly right. So when we look at channel bus bar, and the water actually goes right through the conduit. It is not going through any kind of jacket or anything other within the transformer. So it's actually quite an ingenious way on how we cool our transformers, because we're directly cooling the hottest portion of the transformer.
So does this method of cooling have anything to do with the size of our transformers versus even some other water-cooled transformers?
That's great. So one of the comparisons that we make is between air-cooled and water-cooled transformers. Because of the heat-carrying capacity of water, we can make our transformers so much smaller.
Interesting. So we've kind of discussed this a little bit, but why don't you kind of give us some of the bullet points on the real advantages of using a water-cooled transformer in your system versus, say, an air-cooled transformer?
So because of how a component needs to be cooled, with air, for example, that air has to be constantly circulating around that hot component. In environments where there's a lot of debris and byproducts, harsh byproducts of your application, it can require more maintenance and earlier failures because that air channel is being clogged. Whereas with our water channel, we have it's a closed system, so that none of that debris or clogging can happen. Additionally, air-cooled devices use ambient air to cool them. And so in hot areas like furnace factories or glass applications where the ambient heat is a lot hotter, there has to be special considerations.
Sure.
With our water-cooled transformers, we can pipe water in from anywhere and generally stay at a reasonable temperature.
Well, another consideration that just pops into my mind is because this is totally enclosed, you're probably going to see a lot less maintenance that you'd have to do on this transformer versus, say, an air-cooled transformer where the coils themselves are pretty much exposed to the elements, and thereby meaning you have to keep them clean so that they do release that heat.
Yes, absolutely.
So I have a lot of customers that when I tell them we use water-cooled transformers, they're a little standoffish because in their minds water and electricity don't mix. What do you have to say to that? How do you respond to that?
Hey, that's a great question. You always see the classic picture of a guy holding a toaster over a bathtub, and this
sounds like Groundhog Day.
It does. So that's a great question we get all the time. How are we pumping water directly through our secondary and it's not dangerous? And the simple answer is that water actually acts as a dielectric in these conditions. So water has a great insulating properties. And when you have your transformer properly connected and grounded, it virtually poses no risk if used properly.
We touched on this a little earlier, but I'd like to kind of get into a little bit more detail on this particular question, specifically because this is a huge issue in a lot of plants that are always trying to improve and save money. What makes using a water-cooled transformer so much more efficient than other types of cooling systems?
So imagine an air-cooled transformer and the channels in which the air has to flow through the transformer. The larger area within a transformer forces you to use more magnetics or core to transfer the same amount of electromagnetic energy. When we use water cooling, we're able to make our transformer so much more compact. And when we make it more compact, we can use smaller magnetics and really just kind of shrink the footprint of it. So it's just a whole different type of philosophy of design.
So water itself is significantly more efficient than air to cool a transformer, and it also makes the transformer itself smaller. So, okay, that's very interesting. Now, with anything, I'm sure there are possibly some downsides. Do you have any thoughts on that?
As with any technology, there are always trade-offs. So with water flow, customers have to be very concerned about or focused on how much water flow they're getting through their process. RoMan thinks ahead of this process by installing thermocouples and thermal switches within the transformer itself. And this will identify the process manager that there's something going on that's not getting flow, the transformer is overheating. On the other hand, customers themselves will place flow switches, flow meters in somewhere along their process. And in that way they can identify if there's any lack of water flow and leading to an overheating situation. And finally, one of the trade-offs with water is that if you're concerned about green energy, you could imagine how much water would flow through this transformer in a given process. What we'll see often is customers will use water chillers to recycle their water flow so that it's not being wasted.
So then they can just recirculate it back into the system.
Yeah, that's right.
Okay. Well, I appreciate your time, Dave. I think this is an important topic. I think it's one that impacts our customers' bottom line by improving efficiency and lowering some maintenance costs. As with anything, when you talk about something and answer questions, it usually begs other questions. So if you do have other questions, please feel free to leave those in the comments section of this video. And before we get into our next topic on our next video, we'll start off by answering all of the questions that are posed to us in the comments here. So again, David, thank you very much and have a great day. And to everyone watching, we appreciate you as well.
Thank you very much.